Today we're going to be talking about how to find the power series representation of a function and the associated radius and interval of convergence for the power series. And in this particular problem, we've been given the function f of x is equal to x divided by the quantity 9 plus x squared. So the first thing we need to do is find a power series representation of this function. And the way that we're going to do it is by comparing it to this well-known power series, the power series x to the n power. We know that the sum of that power series is 1 divided by the quantity 1 minus x. So what we're going to do is compare our original function, our f of x function here, to the sum 1 divided by 1 minus x, because they're already somewhat similar. They're both rational functions. We've got two terms here in the denominator of each, one term in the numerator of each. We're going to compare those two together, try to make our function f of x look more similar to this sum here, 1 divided by 1 minus x, and in that way hope to find a power series representation for our function f of x. So in order to make our function look more like this sum, 1 divided by 1 minus x, the first thing we want to do is factor an x out of the numerator of our original function. So if we take an x out and we say that this is x times 1 divided by 9 plus x squared, we haven't changed the function at all. We just factored the x out of the numerator. But now what we have inside the parentheses here, we have 1 in the numerator just like we have 1 in the numerator of this sum 1 over 1 minus x. So we're already closer. Now what we want to try to do is get a value of 1 for the first term of our denominator. And the way we're going to do that is by factoring out a 9 from our denominator. So this is going to become here now x times, and then inside the parentheses we'll still have 1 in our numerator, but in our denominator we'll factor out a 9, and we'll get 9 times 1 plus, now in order to make this still true, what we have to do is call this x squared divided by 9. That way, when we multiply x squared divided by 9 times 9, our 9's cancel and we're just left with x squared, which is what we had originally here, just this x squared term. So that's the way that we keep that still true. But now if we factor this 9 outside of the parentheses, what you can see we have is x divided by 9 times what's inside our parentheses here, 1 over 1 plus x squared divided by 9, like that. Now we're really close to this sum. We have 1 in the numerator, like our sum over here, 1 over 1 minus x. We have our first term in the denominator as a 1, just like this sum over here. The only difference now is the second term in the denominator and the fact that this sum has a negative sign here in the denominator versus our sum, which has a positive sign here in the middle of our denominator. So what we're going to do is, instead of this positive sign here, we're going to turn this into a double negative. We're going to say that this is equal to x over 9 times 1 divided by 1 minus, and now we're going to call this negative x squared over 9, like this. What that does for us is it has this negative sign here. Now what we can just do is say that this x value right here, the x value in this particular spot in this sum, is equal to this x value that we have here, the x value in the same spot. And if we just say that x is equal to negative x squared divided by 9, everything else is the same. So we can substitute this negative x squared plus 9 in for x right here, because in this sum, this infinite sum here, they're pulling this x value from this sum right here, this x value. So when ours is negative x squared over 9, we just plug that in right there. We multiply by x divided by 9, and now we have a power series representation. So our power series representation is going to be the sum from n equals 0 to infinity, and we're taking this directly from the well-known power series here. And then for x, we're substituting negative x squared divided by 9. So we're going to say negative x squared divided by 9. That's all raised to the n power according to our well-known power series here. So now we've represented this part right here, this 1 over 1 minus x, which we had right here inside our parentheses. But we haven't accounted for this x divided by 9, so we have to multiply this by x over 9. We just put that out in front. So this is our power series representation. All we have to do is simplify it, and the way that we're going to do that is by bringing the x divided by 9 inside the infinite sum here. So we're going to say that this is going to be the sum from n equals 0 to infinity. we're going to bring the x divided by 9 inside. We're going to basically have x to the first power divided by 9 to the first power, right? Both of these are raised to the first power. And then here for our negative x squared divided by 9 all raised to the n power, the first thing we want to do with that is pull out the negative 1 value. We can pull out this negative here as a negative 1 raised to the n. Whenever we have a negative value inside parentheses like that, we can pull it out. We just want to make sure it's raised to this exponent here. So we have negative 1 to the n. What that leaves us with is just everything left inside our parentheses, x squared divided by 9. So we get x squared divided by 9. We just need to make sure that we keep it raised to the n power, so to the n power like that. Now, if we simplify further, we'll say we have the sum from n equals 0 to infinity. We'll bring the negative 1 to the n out in front. That's always a good idea, negative 1 to the n power. Now notice here we have x raised to the 2 raised to the n power. Whenever you have two exponents like that, something raised to an exponent raised to another exponent, you can multiply those exponents together. So this is going to become x to the 2n power. Same thing here, you basically have 9 to the first power raised to the n. You multiply 1 times n and you get n. So this is 9 to the n instead of 9 to the first raised to the n. So now we have things with like bases that we can combine. So we have here x to the first power, and we have x to the 2n power. Whenever you have two terms with like bases, they both have a base of x, you can combine them as long as you add the exponents together. So we have an exponent here 2n and an exponent 1, so we can combine these and say x to the 2n plus 1. We just add them together. Same thing here with our denominator. We have 9 to the first power and we have 9 to the n power. So we can combine them and we can say this is divided by 9 to the n plus 1. We just add those exponents together. Now we've simplified this as much as we can. This is our power series representation of the original function f of x. So we've got the first half of the problem done. Now all we need to do is find the associated radius and interval of convergence for this power series. The easiest way to do that is to find the radius of convergence first and then use that radius to find the interval of convergence. The way that we're going to find the radius of convergence is we're going to use the ratio test. And what the ratio test tells us, we're going to call this L. We're going to set that equal to the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. This is the ratio test right here. What it tells you is that if you evaluate this right-hand side based on your power series up here, and you find a value for L, you get some value of L. If you set that value of L to be less than 1, that tells you where your series will converge. So this is an extremely useful convergence test for us to use to find the radius of convergence. All we need to do, we're going to say L is equal to the limit as n goes to infinity of the absolute value. Here for a sub n plus 1, we just plug n plus 1 into our original power series here everywhere we have n. So we say negative 1 raised to, instead of the n plus 1, then we multiply that by x to the 2 times the quantity n plus 1 plus 1. So here we're going to get 2 times n plus 1 plus 1. When we plug n plus 1 in for this value right here, we get 2n plus 2 plus 1 or 2n plus 3. So we have x to the 2n plus 3. Then we divide that by 9 to the n plus 1 plus 1 or 9 to the n plus 2. That's a sub n plus 1 right here that we got. We divide that then by a sub n, which is just our original series here, this whole thing right here. We divide that by this part right here. But because we have a fraction divided by a fraction, instead of just dividing, we can kind of combine two steps here. And instead of dividing by this value, we can multiply by the reciprocal. So then instead of a big division problem, we get a multiplication problem instead. So we just take the reciprocal. In other words, we flip this upside down. Our denominator, 9 to the n plus 1, becomes our numerator, 9 to the n plus 1. And our numerator, negative 1 to the n, negative 1 to the n times x to the 2n plus 1, which was our numerator, becomes our denominator. This is the limit that we're going to be evaluating. From here, we just need to combine like terms. So we're looking for things with like bases. We're going to say L is equal to the limit as n goes to infinity of the absolute value. Now from here, we're looking for like bases, like I said. So we have this value here, -1 raised to the n plus 1 in our numerator, and we have -1 raised to the n in our denominator. Because we have like bases, we can consolidate these terms. We just need to subtract the exponent in the denominator from the exponent in the numerator. So the exponent in our numerator is this n plus 1 right here. So we're going to get n plus 1 from the numerator. The exponent in the denominator is n, so we're going to subtract that exponent in the denominator, so minus n. N plus 1 minus n, our n's are going to cancel, and we're just going to be left with +1. So we're going to get -1 raised to the +1 power in our numerator, or just -1. So we'll get a negative sign here to represent that in our numerator. When we take x to the 2n plus 3 minus x to the 2n minus 1, we subtract those exponents. Our 2n's are going to cancel. We're going to get 3 minus 1, which is just 2. We're going to be left with positive x squared here in our numerator. Then same thing here, 9 to the n plus 1 over 9 to the n plus 2. When we subtract the exponent in the denominator from the exponent in the numerator, our n's will cancel. We'll be left with 1 minus 2, or just -1. So we have 9 to the -1. We know because we have a negative exponent that that value is going to be in the denominator, and we have then 9 to the +1 in the denominator. So this is our simplified absolute value here. Now, because we were able to cancel all of our n values out of this function, this limit as n goes to infinity becomes irrelevant. It's only relevant if we have an n value left over, but we don't have any n values, we only have x values. So this limit as n goes to infinity really just goes away, and what we are left with is that L is equal to the absolute value of -x squared divided by 9. Because we have these absolute value brackets, we can cancel out this positive sign and just say the absolute value of x squared over 9. Remember that we said at the beginning, when we started this ratio test process, that once we found a value for L, we would set it less than 1, and that would give us our radius of convergence. And it does give us our radius of convergence. We just need to solve this inequality for a value of x, and right now we have x squared divided by 9. So what we're going to do is multiply both sides by 9, and we'll be left with the absolute value of x squared less than 9. We get 9 times 1, which is 9 over here. In order to get rid of our absolute value bars and take the square root of this x squared value just to get x on its own, we need to say that x is greater than -3 and less than +3, right? When we take the square root of x squared, we get x. We get +3 over here. Taking the square root means we could also get -3, so we have to say x is greater than -3. This value now that we just found, this x less than 3 right here, this gives us our radius of convergence. It tells us that our radius of convergence is r equals 3, because once we solve for x, whatever value we get right here is our radius of convergence. So now our radius of convergence is 3. We can say that our interval of convergence is -3 to +3. We just take both sides of this inequality here. And this is fine, except that we have to test the endpoints of the interval of convergence to see whether or not the value -3 itself is included in the interval of convergence, and whether or not the value +3 itself is included in the interval of convergence, or if the values between them are the only values for which the series converges and the endpoints actually aren't included. In order to test the endpoints of our interval of convergence, we just want to plug the endpoints into the power series representation that we found earlier of our function. We're going to be plugging in those endpoints for x, not for n, but for x. So let's start with -3. Let's plug -3 in for x. So with x equals -3, here's what we're going to get. The sum from n equals 0 to infinity of -1 to the n power, here's where we plug in -3, so we get -3 raised to the 2n plus 1 divided by 9 to the n plus 1. And really, this is just going to test our skills with algebra and exponents. We just need to simplify this function and determine whether or not this new series right here converges or diverges. And we can use any convergence test that we want to figure out whether or not this series converges or diverges. But before we do that, we want to simplify it as much as we can. So in order to simplify it, the first thing we need to realize is that we can reverse the process we used earlier with exponents. Remember that we said when we had terms with like bases, we can combine them by just adding the exponents together. Well, we can separate them by just separating the exponents. So here we have -3 raised to the 2n plus 1. We can separate these and say -3 to the 2n times -3 to the first power here. We can do the same thing in the denominator. We have 9 to the n plus 1. We can call this 9 to the n times 9 to the first power. So times 9 to the first power, like this. Similar thing here, we have -3 raised to the 2n power. Remember how we said if we had some base here raised to an exponent raised to another exponent, we could multiply those exponents together. Well, here we have the product of two exponents, 2 and n. We can separate those, and instead of saying -3 to the 2n, we can say -3 squared raised to the n power. And we should probably put parentheses around this, but now essentially what we have is -3 squared, which is 9 raised to the n power, so this is going to become 9 to the positive n. From here, we can cancel. We have 9 to the n in the denominator and 9 to the n in the numerator, so those all go away like this, and what we're left with is really just the sum from n equals 0 to infinity. Here we have -3 to the first and 9 to the first power, so we're just left with -3 over 9, or -1/3 times -1 to the n. What we should be able to see here is that this is just a geometric series. Remember, geometric series comes in the form a times x raised to the n power. Well, here our value of a is -1/3, that coefficient. Our x value is this -1 raised to the n power. Remember that the geometric series test says that the series converges if the absolute value of x is less than 1. Well, our x value is this -1 right here, so we say the absolute value of -1 less than 1. We take the absolute value of this, we get +1 less than 1. Well, this is not true. So what we know is that at the endpoint -3, the series diverges by the geometric series test. So we're just going to say for this endpoint, the series diverges by geometric series test. So what that means, because the series diverges at this endpoint, it means that we leave this interval of convergence with a parentheses on this left side here. If we found that the series converged at this -3 endpoint, then we would replace this parentheses with a hard bracket like this. But because it diverges, we just leave this parentheses here. Now we have to test the other endpoint, +3. So we say at x equals +3, what do we get? Well, we have the sum from n equals 0 to infinity of -1 to the n power. Here's where we plug in our +3. So +3 goes in here for x, +3 raised to the 2n plus 1, divided by 9 to the n plus 1. And we have the same process here with algebra. We're going to call our denominator, instead of 9 to the n plus 1, we're going to call it 9 to the n power times 9 to the first power, like this. In our numerator, instead of 3 to the 2n plus 1, we're going to get 3 to the 2n times 3 to the first power. We're going to, instead of 3 to the 2n, we're going to call this 3 squared raised to the n power, and then instead of 3 squared, we're going to call this 9, so this is going to become 9 to the n. We're going to get 9 to the n and 9 to the n to cancel from our numerator and denominator, and you can see that all we're left with is the sum from n equals 0 to infinity, -1 to the n power. We're just left with 3 divided by 9, or 1/3. We can put that 1/3 out in front there. It's the same as what we had before, except +1/3 instead of -1/3. But the fact remains that this value here that we had for x, because this is a geometric series, is unchanged. We're going to get this same inequality here. The absolute value of x less than 1, we're going to plug in this -1 value for x, and we're going to find that 1 is not less than 1. They're equal to each other. And so by the same test, we're going to say diverges by the geometric series test. So both endpoints, the series diverges at both endpoints, which means we leave the interval of convergence written this way with these soft parentheses instead of hard brackets like this. So this is our interval of convergence, this is our radius of convergence, and this is our power series representation here that we found for the function f of x.